Talk about, and we looked at this last year, Leo, many body problems. Problems where you have more than one mass connected by strings. Here is the key shortcut that we can take. If the objects are attached by strings, they're going to accelerate at the same rate. Sorry for those of you on YouTube, you can't see the demo I'm doing. We're going to say that even if this ball and this ball are accelerating in different directions, if this is accelerating up at 2 meters per second squared, this one is accelerating to your left at 2 meters per second squared. The magnitude of the acceleration will be the same. What we're not going to let you do is jerk on the string so that we have a differing acceleration. It's actually called a jerk, and it turns out the physics of a jerk is actually surprisingly difficult. Those of you in calculus, I'll be able to give you a better explanation of what a jerk is in about a month or so. So I said the easy approach is to realize that we can treat this system as a single object since all parts are accelerating at the same rate. It says find the acceleration and find the string tensions. You know, this is a good job for a free body diagram. Although, did they give me a picture? I'm going to label the picture rather than do a completely separate free body diagram. So I'm going to start, I usually just start from the left and go from left to right. What are the forces acting on the 6 kilogram mass, Leo? Get the obvious one. What are the forces acting on the 6 kilogram mass? Get the obvious one. Gravity. We go systematic. Now, is there more than one mass in this question? Say yes. So instead of just writing mg, I'm going to write m1g. I'll call the second mass m2. If there's a third mass, m3, etc. I usually go from left to right, so the first one you'll see will be m1, the next one you'll see will be m2. There's no rhyme or reason. You could have called the right-hand mass m1 if you wanted to. Is m1 sinking into the ground like quicksand? Is it flying here like Superman? So we're going to have a normal force, and Leo, I'm going to call it normal force 1 to go with mass number. Yeah. What else? There's a rope. What do we call the force from a rope? Starts with the letter T. You're feeling it right now. Yeah, I'm going to have right there tension, and I'll just draw the arrow right on the rope. Is there friction in this question? No, it says frictionless surface, although it wouldn't be that hard to add one more force pointing that way to our left. We could, in fact, we will in the next example. Yeah, those are the forces acting on the first mass. What are the forces acting on the second mass? Get the obvious one. We're going to have m2g. Good. And we're going to have normal force number 2 to go with mass number 2. And I think normal force number 2 is the same size as m2g. What do we call that 40 newtons, the mystery force coming from off the page? What name did we decide to give that? Yeah, this is going to be F applied. I'll draw a little arrow and I'll put F applied equals 40, so I noticed that I noticed it. We're missing one more. Which force are we missing? Tension, which way? Yeah, there's going to be tension, no friction here because it's a frictionless surface. We'll bring friction in the next example. These two tensions, this is a consequence of Newton's third. Forces come in pairs. If the rope pulls on one, the other one pulls back through the rope on the first mass. Okay, we've got our setup. Leo, which way do we think this thing is going to accelerate? I think to the right. In fact, I know it will because we're on ice and there's an unbalanced force pointing this way. So which way is the winning direction? Same answer, to the right. What we're now going to do is we're going to write an equation, but our equation is going to be along the rope. We're going to walk the entire length of the rope. So starting over here, who's winning? Good. And anything pointing to the right is going to be winner plus. Anything pointing to the left is going to be loser minus. So I'm going to write my equation right here. It's going to be F applied, and then I walk along the rope. I don't care about M2G. I don't care about normal force number 2. They're not along the rope. Oh, this tension here pointing to the left, loser minus. Ooh, this tension here pointing to the right, winner plus. Are there any more forces along the rope? Equals. And then here was the tweak. We said because I have forces from more than one mass on the left, I have to have more than one mass on the right. It's going to be M1 plus M2 times A. Although last year I didn't write M1 plus M2 in brackets, I wrote it even shorter. Who remembers what I wrote last year as my abbrev? I said M something A. Yeah, M all. If you want to, I'll do it in red. You can write above it. That was M all A. In this case, it's M1 plus M2. If there was 3 masses, it'd be M1 plus M2 plus M3, M all times A. Nicole, put your pencil down. Tired girl. Stretch. Put your pencil down. Stretch. 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 Why are we stretching, Nicole? Why are we so relaxed? What do we like about these questions? It's the terrible joke from last year. Oh, we're losing tension. So if we're losing tension, we must be more relaxed. We've got to relax. We're losing tension. We're stretching it out. A little more awake now. It wants me to find the acceleration. Leo, how would I get the A by itself? How will I move the bracket over? Yeah, that's a terrible looking M. Let me redo that. And we actually end up with a pretty clean equation. It turns out it's going to be F applied divided by M1 plus M2. If I hadn't included friction, I just have more stuff on the top. What was F applied as a number, Leo? What was M1? Good. M2? You might even be able to do this in your head without a calculator, because I think it's 40 divided by 10. What? Yeah. Meters per second squared. Let me pause the video for a second. Hang on 1 second. So our strategy was, if you want to meet, listen close, to find the acceleration of everything, I wrote an equation for everything. Okay. What does part B want me to find, Nicole? You have to go up a little bit, but what does it say for part B? Tension. To find an individual force, I'm going to write an equation for an individual mass. Why can't I use this equation to find the tension? Be fairly stupid obvious. The tension's canceled, and I think I gave you the terrible joke last year. I said we have attention deficit disorder because we have a deficit of tensions. We're missing the terrible joke from last year. It's a terrible joke. Anyways, so what we're going to do is we're just going to look at a single mass. I'm going to quickly resketch the 6 kilogram free body diagram. It was M1G, normal force 1, tension. Leo, let's you and I keep going. Looking only at the 6 kilogram mass, which way is it accelerating? To the, starts the letter R. Who's winning? It's only one arrow pointing to the right. Don't overcomplicate it. Who's winning? I don't know what one that is. Tension. Who's losing? It's a trick question. Losing would be pointing that way. Who's losing? More specific, is there anything pointing that way? No, tension's pointing to the right. Is there anything in this diagram right here, is there anything pointing to the left? No. So who's winning? Tension. Who's losing? It's a trick question. What? No one. Good. Winner, no loser, equals, oh, now we're only looking at one mass, so it's not going to be M all A, it's going to be M1A. It's going to be, oh, what was M1? 6. What was A? Just dropped it down. 4. What's the tension? Maybe in your head without a calculator? 24 newtons. So let me say the magic phrases again. To find the acceleration of everything, I write an equation for everything. To find an individual force, I write an equation for an mass. And the nice thing is, it doesn't matter for this tension which mass I picked. I picked M1, and I got T equals M1A, easy to solve. I could have picked M2. M2, I have M2G, normal force 2, F applied, tension. You all have the free body diagram up there as well, but right here. And I would have said, who's winning? Who is winning, Callum? Who's the loser? equals M2A, because I'm writing an individual mass for an individual force. So it would be F applied minus tension equals M2A. Callum, what's right in front of the tension that I don't like? We'll do the swappy dance. And many of you in your prime last year were at the point where you could almost do this in your head. I'll plus the tension over, and I'll minus the M2A over, and I'm going to get tension equals F applied minus M2A. It's going to be 40 minus 4 times 4. What would be really cool would be if that also worked out to 24 newtons. Does it? Put your calculator away, Callum. It's 40 take away 16. Does it? Yes, it does. 24. 40 take away 16 is also 24. And so the nice thing is, for many body problems, if you're finding individual forces, pick the one that's the easiest, is what I do. I kind of quickly do both free body diagrams in my head, whichever equation is the cleanest, usually, or that I'm the most confident in. Maybe there's one that has less writing, but that force I'm not sure about, I avoid it. What if we have several masses connected by strings? What if we have 3 masses? We need to realize that if we have more than one string, we have more than one tension. So it says find the acceleration, find the chord tensions. Anybody want to guess what this might be a good job for? A free body diagram. So Cairo, let's see. Ooh, and they want me to include friction. Okay, let's jump all the way in. Cairo, what are the forces on the 3 kilogram mass? Get the obvious one. Get the obvious one, don't forget. Let's go systematic. I'll call that M1G. I'll call the second mass M2 and the third mass M3. Is M1 sinking into the ground like quicksand? No, we're going to have a normal force the same size as M1G. I'm going to call that normal force number 1 to go with mass number 1. Is there a rope? So tension. Oh, is there more than one rope? Yeah, I'm going to call this tension 1. I'll call the other rope tension 2. Is there friction? Yeah. I think friction is pointing this way. I'm going to call that friction force number 1 to go with mass number 1. What about the second mass? What are the forces acting on it? Let's go systematically. Get the obvious one. Good. What else? I'll call that M2G. Normal force 2, yes? Is tension 1 slowing it down? Yeah, so I'm going to have tension 1 pointing that way. Oh, is there another rope? I guess I'll call that tension 2. Which one have we missed? Friction here too. I'll call that friction force number 2 to go with mass number 2. What about the third mass? Get the obvious one. M3G. That's a terrible looking 3, Mr. Dueck. Normal force number 3. What are we going to call this 20 newtons coming from off the page? F applied. We're missing 2 forces. Which ones? Tension 2. And I'll call that friction force number 3 because it comes from mass number 3. I think I used the phrase last year, we're going to be lazy but organized. I think we got everything. Which way is this accelerating? Probably to the right. I think that 20 newtons is winning. I'll know it wasn't winning if when I solve this, I get a negative acceleration. But for now, let's assume this is the winner. And again, we're going to walk along the rope. So, Cairo, who's winning? Okay. I've had to scroll down. I think we run into tension 2, but it's pointing to the left, so it's a loser, yes? And I think we went into friction force number 3, and it's also a loser, pointing to the left. Oh, but then we run into tension 2 again, but this time it's pointing to the right, winner plus. Then we run into tension 1, loser. Friction force number 2, loser, minus. Then I run into tension 1 again, but this time it's a winner plus. Help me out if I'm missing any. I'm going from memory. Oh, what's the last one I got to include? Friction 1, loser minus. Have I reached the end of the rope? And again, notice M1G, M2G, M3G, not in my equation. I'm writing an equation for the rope. What's that going to equal? M all A, where M all is M1 plus M2 plus M3. But that's less writing, so I'll go with that. How's your day been, Cairo? Put your pencil down. Stretch it out. Why are we relaxing? Twice. Wow, this is really relaxing. We lose tension here. We lose tension here. It's like spa treatment. I love it when I lose tension. While we're at it, how would I get the A by itself? By? If I divide by A, if I put the A on the bottom, then I'll get the A by itself. I think I disagree. What do I want to divide by to get the A by itself? Yeah. Okay. So I'm going to write it all out here. It's going to be A equals F applied minus, instead of writing friction force number 3, friction is what times what? So it's going to be mu normal force 3, and then minus mu normal force 2, and then minus mu normal force 1, all over M1 plus M2, M all, M1 plus M2 plus M3. Problem, Cairo. I don't know normal force number 3. Or do I? I think I said last year, I don't know M3G. Oh, but look. I don't know the forces. Sorry, I don't know at normal force 3. Oh, but it's going to be M3G, yes? Because we're not on a slant or anything. M2G at M1G. I don't want to rewrite this. I'm fine if, to show your work, you did something like M3G, M2G, M1G. That's pretty good. That's clear to me. That's lazy, but still organized. F applied was 20 minus 0.2 times 5 times 9.8 minus 0.2 times 2 times 9.8 minus 0.2 times 3 times 9.8 all over 3 plus 2 plus 5. Do that one in your head, Mr. Dueck. Well, maybe. I can factor out a 9.8 and a 0.2, so it's going to be, maybe it's going to be a 10. 1, 2 times 10. Just 2. 9. Oh, yeah. It's going to be 19.6. It's going to be 4 on the top. Divided. Is it 0.4? Yeah. It's a fluke that it worked out to really nice numbers, but I'll take it. No, am I wrong? 0.04. I carried a decimal wrong. 0.04, Mr. Dueck. Oh, you could have been so proud of yourself, but you botched the 0. Wow. Cairo, is that a big acceleration? No, this is barely sliding. Much more mass, and that 20 wouldn't be enough to get it moving. Okay. That was part A, and then B said find the chord tensions. Let's use the 3 to find tension 1 because I think it's the cleanest. I'm going to quickly sketch the free body diagram. I have M1G, normal force 1, tension 1, friction. Tayshawn, if I write an equation for mass 1, who's winning? First of all, which way is mass 1 accelerating? To the? So who's winning? To the right. Which force is pointing to the right? Tension 1, because there's two of them. I got to be a little careful. Who's losing? Yeah, this time, Leo, there is a loser, friction pointing in the opposite direction. So we've gone one past yours. It's going to be tension 1 minus friction 1 equals M1A. If I want to get the T by itself, it's going to be M1A plus friction 1. Tayshaun, friction is what times what? So it's going to be mu normal force number 1. I don't know normal force number 1. Oh, but look, it's M1G. So now I would probably say, hey, that can be M1G. Go ahead. Hey, I think we're good now to plug and chug. Let's see. Tension is going to be M13, 8.04 plus what's mu? I don't know what's mu with you. 0.2 M13, 9.8. What do you get? Not 0.3, Mr. Dueck. 3 times 0.04 plus 0.2 times 3 times 9.8. Hey, Sean, what'd you get? Oh, he's reaching for his calculator, finally. Holy smoke, is 6 even? Take that. Okay. We need to find tension 2 as well. Which mass looks less cluttered, the 2 kilogram mass or the 5 kilogram mass? Or which mass would I use to find tension 2 if I had a choice? Why might I not use the 2, the middle one? To find tension 2, I would need to use tension 1. If I got tension 1 wrong, what? I'm going to get tension 2 wrong. So I think I'm going to use this one. My equation's going to be winner, F applied, minus tension 2 minus friction 3 equals M3A. I got to do that on the next page. I'm not going to do the 2 kilogram mass. It's a bit yucky. I'm going to do the 5 kilogram mass. What did I say we had? We had M3G, normal force 3. We had F applied, tension 2, friction 3. So it's going to be winner minus friction 3 minus tension 2 equals, why just M3A? We're writing equations from only one mass. Maddie, what am I trying to find? Which one? What's right in front of the tension 2 that I don't like? Ugh. Wait a minute. Swappy dance. Plus that there, minus that there. And I'll get F applied minus friction 3 minus M3A, and I'm going to write the tension equals over on this side because that's where we're used to seeing the thing by itself. It's going to be F applied 20 minus mu M3G. I've done that a couple of times. I just lifted that right from the previous examples. Minus M3A. And now I can plug and chug. Here we go. It's going to be 20 minus what's mu? 0.2 m 5g 9.8 minus 5 times 0.04, yes? That's a 0.
Okay.
10 even? Yeah. Oh, these are nice. Newtons. Anyone else? Let's get some confirmation here. Yeah, got a 10? Sorry, people are still writing. Losing some tension, Raisa? Yep, me too. We'll pause here a little bit. We'll finish this off next class. But if you want to get a head start, you're capable of doing number 1. Number 1 and number 2 are identical. If you get number 1 right, you can skip number 2. You can skip number 3. 4 is good. I'm going to assign 5 next class, but you can try it. 7 is good. 8 is good. 9 is good. 10 is good. 11 is good. 12 is good. 13 is good. But you're going to get some time to work on this next class. You can skip 14. You can try 15. 15 is a missing mass question. I did them with you last year. I haven't reviewed it this year. That's going to be part of lesson 5, the Atwood machine. So the ones that I've assigned, this is not due next class. I'm going to finish this lesson off next class, and so then we'll work on all of this. But I said you can try 1, 4, 5, 7, 8, 9, 10, 11, 12, 13, skip 14, 15. So the ones that I crossed out 6, I crossed out 3, I crossed out 2, and I think I crossed out 14. Let me hit pause the video for a second.